Alright guys, this is your help video for your Unit 1 study guide. I'm going to do all the even problems. Those are the ones that you're required to do. I've also included odd problems that match the even problems that come after them in case you want a little bit of extra practice. And the answers for the odds will be included on your study guide. So let's go ahead and get started here. We'll go ahead and begin with number 2. All right, so number 2, the problem is asking us to find the average rate of change. And if you guys forgot what that is, you don't have to draw this, but I'm going to draw a graph really quick. Imagine there's like a curve, okay? And the average rate of change from this point to this point can be found by finding the slope of that line, which is called a secant line. Okay, so our goal is to find the slope of the secant line between 2 points. Now what they're going to be giving you here are 2 x values. This is your first x value and this is your second x value. And our job is to find the slope of the secant line that goes between those 2 points. Now the way that you find the average rate of change, or the slope of the secant line, is by using the old Algebra 1 slope formula. y2 minus y1 over x2 minus x1. Now the problem gives us our x1 and x2, so we could just plug those in right now. But we have an issue here. If we want to find our y values, we don't have those, but we can find them. And here's how you find them. If you want to find y1, all you have to do is plug the x1 into your equation here. So here's my x1. I'm going to go ahead and plug that in. So that would look like this. y1 is equal to x1 plugged into my equation. So here we go. 0 squared is 0. Always do your exponents first. And then multiplication if there is any, but in this case I don't have any. And then addition. So that's 1. So my y1 is 1. To find y2, we're going to plug in the x2 value. So I'm going to take the x2 value and plug that in to my equation. So y2 is going to be 1 squared plus 1. Exponents first once again, and then addition. And so my y2 is 2. So now that I have my y2 and y1, I can plug those in. y2 minus y1. So that means my top is 1, the bottom is 1, and my final answer is 1. That would be the slope of my secant line, also known as the average rate of change on the interval that they gave us. All right, let's go ahead and jump on up to number 4. Number 4 is asking us to find the slope of the secant line that goes through these 2 points here on this function. All right, now you might notice something a little interesting. How do you know if these are points or if they're an interval? Because like on number 2, that almost looks like a point, doesn't it? It's not. So one way you can tell is because they're giving you brackets, okay? But another way you could tell is because, let me close this out really quick. On numbers 3 and 4, they tell you that these are given points. So in other words, this is an x and a y, this is an x and a y. Whereas up here on numbers 1 and 2, that's not a point because they tell you that's an interval. Okay? Now intervals are always x values, points are x and y's put together. Okay? So that's how you can tell the directions kind of indicate what we're looking at. So we want to find the slope of the secant line that goes through these 2 equations. Now, how do you find the equation of a secant line? Well, you find the equation of a secant line the same way that you find the slope of a tangent line. You need an x, you need a y, and you need a slope. Now, we have 2 different groups of x's and y's up here. We have this pair, and we have this pair. And since we have 2 of them, I'll call the first set the 1s and the second set the 2s. Now, when I'm trying to find the equation of my secant line, I only need one of the x values, so I think I'll pick the one that's not negative. Let's go with this one. So if I pick that x value, then I have to pick this y value that goes with it. So that's going to be the x and the y value that I'm going to use. Now, if I wanted to find the slope, well, since we're doing a secant line and not a tangent line, once again, we're using this formula. So let's do that. y2 minus y1 over x2 minus x1. Double negatives become a positive, and I end up with negative 3 over 3, which is negative 1. So there's my slope, there's my y, there's my x. So if I want to write the equation of my tangent line, I just need to plug it into this thing. Yep, it's the same formula that we use for tangent line, because this is really just a formula for any linear function. The only thing that makes this one special is that it's a secant line, and we know it's a secant line because we have an average rate of change, which is just found by doing the regular old slope formula. So here we go. Negative 1, parentheses, x minus x1, which I decided to go with the 1 and the 4 on that one. y1 is 4. This is an acceptable answer, but they might want you to simplify it. If this turns out to be a multiple choice question, which I think it probably will be, then we're going to want to simplify this. Final answer. Okay? So that would be the equation of the line that goes through these 2 points here. And that's that. All right, so this question is asking us to find the instantaneous rate of change of this function. Instantaneous rate of change. Now, an instantaneous rate of change is found in a different way. Okay, it's not by doing the slope formula. Instantaneous rate of change is found by taking the derivative of your function and then plugging in the x value that they give you. So basically, I need to start by finding my derivative. So what is the derivative of this function up here? Well, doing the power rule, I get 4x, and then taking the derivative 2 is just 0, so that just goes away. Next, we're going to plug 0 into the derivative, and that will tell me my answer. So 4 times 0 is 0, and there's our instantaneous rate of change. So an instantaneous rate of change is found by taking the derivative and then plugging in the number, and then you're all done. So let's go ahead and take a look now at number 8. Number 8 is asking us to find the slope of the tangent line, not the secant line, but the tangent line. So tangent line is a lot like secant line. You need an x, you need a y, and you need a slope. Now, once again, in the directions, they said this is a point. So we know that that's x1 and y1. So my x value is negative 2 and my y value is negative 2. But how do you find the slope? Well, you're going to, with an instantaneous rate of change, this is how it's different from a secant line. With an instantaneous rate of change, you take the derivative and you plug in the x value that they give you. Okay? So let's do that. What is y prime? Y prime is 2x plus 2. And now I want to plug in the x value that they gave me. And then we're going to simplify it. So I have negative 4 plus 2, which is negative 2. That's a lot of negative 2s we got going on there. And there we go. So my slope is negative 2, my x value is negative 2, my y value is negative 2. So the equation of the tangent line would be, plugging it into this little formula right here, y equals negative 2, x minus a negative 2, plus a negative 2. And this question, if it does show up on your test, would be a multiple choice one, although there's a lot of questions where I could ask you to find a tangent line. So there might be one on the FRQ also, but for now, this type of question where you're just working with a polynomial would be a multiple choice one. We can simplify this. First of all, these become positives, right? Because double negatives makes a positive. This is just going to become minus, because when you add a negative, that's like subtraction. And then we also need to distribute. So if I were to fix those signs and do my distribution, I would end up with negative 2x minus 4 minus 2. And then we can go ahead and simplify to get that. And that would be the equation of the line is tangent to this function at this point. All right. So the rest of the greater majority of the rest of our problems are all just doing derivatives. So the first problem I have here is just so you guys can practice doing the power rule. Okay, so before I begin, though, we need to rewrite some stuff. This 4x cubed is fine, so I'm going to leave that alone. But this guy, we need to rewrite that before I can start doing the power rule. This is the numerator, and this is the denominator. You're going to write that as a power. We also need to rewrite this guy. Anytime you have a number on the top and a variable in the bottom with a power, we're just going to bring that variable up and put it by the numerator with the same power but negative. Okay, now that I've fixed all those and rewritten them, now I'm ready to go ahead and do my derivative. So the derivative is going to be just the power rule. You multiply that, take one off the exponent, and you're done. Next one, multiply there. 2/5 times 5 is going to be 2. Subtract 1 from your power, and you get negative 3/5. Multiply that to the front, you get negative 6. Take 1 off your power, now it's negative 4. Now it's possible that this would be the answer, but they also might choose to rewrite it. The negative powers might be written as positive and moving the term into the denominator. Also, since this is plus and negative, they're just going to make that minus. Another thing that they might do is they might rewrite this even, and they might make it instead the 5th root of x cubed. That's another possibility. But there we have it. So let's go ahead. That's the power rule. Let's move on to number 12. This is the product rule. How do I know that? Because I've got two functions that are being multiplied together. So here's my a, here's my b, and off we go. The product rule tells me that we do a prime times b, and then add to that a times b prime. So the derivative of a is negative 3x squared. And then we're going to put b in there. I recommend putting parentheses on there. A is negative x cubed plus 5. And then b prime is going to be negative 8x cubed. The derivative of that is negative 8x cubed, and then the 2 just goes away because it's a constant. And we're not going to be simplifying these. We're just going to leave our answer like that. But you do want to be aware of a couple of things. First of all, since multiplication is commutative, what do I mean by that? For example, 4 times 5 is the same thing as 5 times 4, right? It doesn't matter what order you're in. So technically, these two things could be swapped. You could switch those around. Also, addition is commutative. So this entire set and this entire set are connected by a plus sign. So technically, those two sets could be swapped. Okay, but what does matter is that the b is with the a prime and the a is with the b prime, and there's a plus in between them. But other than that, the order doesn't really matter with the product rule. Number 14 is to help you remember to do the quotient rule. Now, how do I know to do the quotient rule? Now, what's an important part of this test is not just knowing each rule, but knowing when to use the rule. You should be able to look at this and know, oh, I need to use the quotient rule. How would you know? Because it's a fraction. Okay. Once you know that, then you're ready to go ahead and apply the quotient rule. The quotient rule is low d high minus high d low. Draw a line, square below. So low d high. D high means take the derivative of the high function, the one up on top. That would be 16x cubed. Minus high, d low. Draw a line and square below. And we're not going to be simplifying that one either. Okay? Go ahead and move on. All right. Number 16, what derivative rule can we apply here? Well, I see that this has an outside function on it. The outside function is something being raised to the negative fourth power. And then the inside function I see is just 5x cubed plus 3. When you see an inside function and an outside function, that's a good indicator that you're going to do the chain rule. And the derivative of a chain rule is going to be the derivative of the outside multiplied by the derivative of the inside. So the derivative of the outside, the green part, would be to take the power of negative 4 and multiply it to the front and take 1 off of the power. The inside will stay the same. The next thing we want to do is multiply that by the derivative of the inside. The 3 is just going to go away because it's a constant, but the derivative of 5x cubed is 15x squared. Now it's possible to simplify these a little bit. I could put this with this. Negative 4 times 15 is going to be negative 60x squared. And then the rest of it we could do this. And since that's a negative exponent, technically we can move that entire set of parentheses into the denominator. So that way it can have a positive power. So that's another possible way to write our answer there. But this may be all I expect of you on the multiple choice, but any one of these are possibilities too. All right, let's go ahead and take a look at number 18. Okay, so what do you guys see here? What rules can we apply? Well, I see two rules. I see something being multiplied by something, first of all. So that's a product rule. I'm going to call this A, and I'm going to call this B. So the derivative of A. Well, if I wanted to take the derivative of A, now I see another rule that I have to deal with. Because A is a composite function. It has an outside and it has an inside. And therefore, to take the derivative of A, I'm going to have to do a chain rule. The derivative of the outside would be to move the power to the front and then to take 1 off of the power, leaving the inside the same. And then multiplying that by the derivative of the inside, which is simply 5. Okay? The rest of it will be pretty straightforward. B won't be changing. It's just x to the 4th minus 3. A won't be changing here. It's going to just be 5x minus 4 to the 4th power. And then finally, B prime, the derivative of this will be 4x cubed. And that's going to be good enough. Technically, they might choose to multiply the 4 and the 5 together to get 20, but I think I'll leave it like this because I don't think people will be simplified on your test, but either way. Okay, let's go ahead and take a look at number 20. What rules do you guys see being used here? Well, hopefully you're seeing, oh, well, I've got a fraction, so I know there's going to be a quotient rule going on here. So let's do that. The quotient rule is low d high. Now I'm going to make that a really long set of parentheses. You'll see why in a minute. Low d high minus high d low. Draw a line and square below. All right, so let's do it. Low is the bottom piece there, so that's 3x to the 5th plus 4. D high, that's the derivative of the top. Now, to find the derivative of the top, you got to understand, once again, we're looking at a chain rule. I've got an outside function, and I've got an inside function. Okay? So to take the derivative of the top, we're going to have to do the derivative of the outside times the derivative of the inside. So the derivative of the outside, that's the green part, would be to move the power to the front and to take 1 off of the power and leave the inside the same. The derivative of the inside would be 6x squared. Next, we're going to do, so that's low, d high. Now we've got minus high. So this is going to stay exactly the same. D low. The derivative of the bottom is going to be 15x squared. Draw a line and square below. And now we're good. So that one was a quotient rule with a chain rule inside of it. All right, let's go ahead and take a look at number 22. All right, so we have another chain rule problem here, but this is a special chain rule problem. What kind of chain rule problem is this? Hopefully you're recognizing that this is a chain rule twice problem, or a double chain rule problem. These are the ones that I compare to an egg. You have the innermost function, which I compare to the yolk of an egg, because it's the most deeply embedded part. Then we have the shell, which is this outermost part. And then everything else is what I call the egg whites. Okay? So let's go ahead and do this. We have yolk, we have whites, we have shell. Multiplying all those together, we're going to end up with our derivative. So let's start off with the shell. The derivative of the shell, well, that shell is just a power function. We have something being raised to the second power. So you move the 2 to the front, you take 1 off the power, and you leave everything else exactly the same. Now let's go ahead and do the green part. Okay, it might help a little bit if we just pretend like the rest of it's not there now, because we already took care of the outside part. So let me erase the shell now. The shell doesn't matter anymore. We did the shell. Let's focus on just the green part now. All right, so for the green part, first of all, that 4 right there is just going to go away. It's a constant. But this guy here, that's a power rule. So we're going to move the 5 to the front, and we're going to take 1 off the power, and we're going to leave the inside exactly the same. So that green part has now had its derivative taken, and it's done. The last thing we need to do is take the derivative of the yolk. So I'm going to go ahead and erase now the egg whites. We've already taken care of the green part, the egg whites, and so all that I'm left with now is that yellow part. And so taking the derivative of that, the 4 is just going to go away because it's a constant being added. And then this guy here, the derivative of that is just 6x. Okay? And so there's our double chain rule. All right, let's go ahead and move on to yet another problem. Number 24. Now we're into the world of trig. Now trig is always going to be treated like a chain rule. Okay? The outside function is going to be the cosecant. The inside function will be this piece here. Okay? So the derivative of the outside is the derivative of cosecant. So if you look at your notes, you'll see what the derivative of cosecant is. The derivative of cosecant is negative cosecant of something times cotangent of something. Okay? And that something is 4x squared. Because remember, when you do the derivative of the outside, the inside does not change. But we do need to multiply this by the derivative of the inside. So the derivative of the inside is going to be 8x. Okay? Now technically you could put the 8x in the front, in between that negative sign and the cosecant. That would be fine if you wanted to rewrite it a little bit different. But either way, that's our derivative. Let's take a look at number 26. We have a secant function. All right. Well, the outside function this time is the secant, and the inside function is the x squared. So my derivative of secant is secant something tangent something, and that something is the inside function, which is x squared. Now we need to multiply that by the derivative of the inside, which is 2x. And once again, if you wanted to simplify, you could technically put that 2x in the front. But that's about all that one can do. Let's move on to number 28. One more trig function. I leave the rest for you guys. If you want to practice more trig functions, try the odd ones. Let's do this one. So this time cosine is my outside function and my inside function is x to the 5th. So if I wanted to take the derivative of the outside times derivative of the inside, the outside function is cosine, so the derivative of that is negative sine of something. And in this case, my something is x to the 5th. Multiplying that by the derivative of the inside, that would be multiplying by 5x to the 4th. And once again, if you want to move that 5x to the 4th, you would put it in between the negative sign there and the sine x. Go ahead and take a look at number 30. Now in number 30 we have trig functions again, but you're going to notice something special. They've got that little -1. So even though that looks just like a cotangent, it's actually not. This is an arc cotangent, and its derivative is completely different than regular cotangents. So make sure you're paying attention to that. This one is in your 1.8 notes if you're looking for how to do these. So arc cotangent, the outside function will be this. The inside function is going to be the negative 4x cubed. I guess we're not using y on this problem, we're using f prime, so I guess I'll start using that. So we're going to do the derivative of the outside multiplied by the derivative of the inside. So look at your notes, and you'll see that the derivative of arc cotangent is -1 over something squared plus 1. And the something, once again, is whatever's on the inside. Then the derivative of the inside is going to be -12x squared. Now let's simplify this a little bit. First of all, on the bottom of this fraction, I can square this. If I square the -4, I get 16. And if I square the x cubed, I get x to the 6th. The plus 1 is going to stay there. Now, on the top, I've got a -1, but I can multiply that by this -12, and the negatives cancel, leave me with just 12x squared. So this would be the simplest answer for f prime. Let's go ahead and take a look at number 32. It's another arc trig function, because there's that little -1 there again. So we have arc cosecant this time as the outside function. And for our inside function, we have 5x squared. So once again, f prime is going to be a chain rule where we have the derivative of the outside being multiplied by the derivative of the inside. The derivative of the outside is the derivative of arc cosecant. And the derivative of arc cosecant is -1 over the absolute value of something multiplied by the square root of something squared minus 1. And the something, once again, is that 5x squared. So that 5x squared is actually going to go in 2 spots. Then we multiply by the derivative of the inside, which is 10x. All right, let's simplify this a little bit. So first of all, anytime your absolute value has a positive number here and an even exponent, you can get rid of the absolute value bars because this has to be positive no matter what, and the absolute value bars aren't going to do anything to it. Now, if you ever have an odd power, or if this number here is negative, then you actually should just leave the absolute value bars on there. Okay? Now, for this piece here, we can simplify that. 5x to the second power squared is going to be 25x to the 4th. And then this 10 can multiply to the 1 on top, giving me -10x. And since I got rid of those absolute value bars on the bottom, we can actually reduce these two numbers. 5 goes into 10 twice, and this x will take away one of the x's off the bottom. So as a final answer, then I have -2 over x square root 25x to the 4th minus 1. Okay? Let's go ahead and take a look at number 34. It's our last arc trig function here. This time my outside function is arc tangent. My inside function is 4x cubed. So if I'm looking for f prime, once again, outside times inside derivative. The derivative of arc tangent is positive 1 over something squared plus 1, and that something is 4x cubed. The derivative of the inside is 12x squared. Simplifying this guy can go to the top to make 12x squared. This guy, if I simplify that, is going to be 16x to the 6th. And that's as simple as that one gets. All right, let's take a look at number 36. On number 36, we're transitioning now to talking about natural logs. So when it comes to natural logs, in this case, for this particular problem, the ln is your outside function, and your x to the 5th is your inside function. So once again, chain rule, derivative of the outside, derivative of inside. Let's go ahead and take the derivative of ln. Now anytime you're taking the derivative of ln, it's going to be 1 over something, and that something will be whatever's on the inside, which is x to the 5th. Then we multiply that by the derivative of the inside, which is 5x to the 4th. And once again, we could put these together. The 5x to the 4th can multiply by the 1 on the top, and we end up with this. And if possible, go ahead and reduce. These 4x's on the top can take 4x's off the bottom and leave us with just 1, and our final answer will be 5 over x. Okay? All right, let's go ahead and take a look at number 38. This is an exponential function. So when you have exponential functions of base e, e will be the outside function, and the exponent will be the inside function. So when we apply our chain rule, derivative of the outside times the derivative of the inside, the derivative of the outside is the derivative of an e function. Now when you're taking the derivative of e is just exactly the same, so it doesn't change a bit. That's the derivative of the outside. It's the same thing as the original problem. But what we do get is a derivative of the inside. That will change a little bit. So that's going to be 25x to the 4th. A better way to write this final answer, if we were to simplify it, would be to put that 25x to the 4th up in the front, and then e to the 5x to the 5th power. That. All right, let's go ahead and move on and take a look at number 40. We've got a log problem here. Now, when you're taking the derivative of a log problem, just like ln, the log is the outside function, and the inside will be this little piece that's in here. Okay. So when we take the derivative outside times inside, the derivative of the log, well, since it's not an ln, it's going to be a little bit different. It's still 1 over something, and that something is still 2x to the 5th, the inside piece. But if it's something that's not a natural log, but a log of some other base, then we also need to multiply the bottom by ln of whatever the base is. In this case, it's 3. Then we multiply that by the derivative of the inside, which is 10x to the 4th. And then we can start simplifying it. Moving the 10 to the top there, 10 times 1 is 10. So the top is 10x to the 4th. The bottom is 2x to the 5th, ln of 3. 2 goes into 10 5 times. These 4x's will take away 4x's off the bottom and leave us with just 1. And so my final answer is 5 over x ln of 3. Now, just so you guys know that this number 3 here is locked inside of this ln. Okay, so you can't reduce that 3 with anything, just in case you were thinking about that in other problems. It just stays down there on the bottom, just like that. Go ahead and take a look at number 42. This is another exponential problem, but this time my base is not an e. So let's see what the difference is there. So now, just like the e problem, the exponential part is my outside, but the inside is this part here in parentheses, the exponent. Right? So derivative, once again, is going to be chain rule. And once again, the derivative of an exponential function is that it stays exactly the same. It doesn't change, just like with e. However, there is a little bit of a difference. Since it's not base e, we do need to multiply it by ln of whatever number's right there. In this case, that would be 3. Okay, so there's that. Now we also need to multiply by the derivative of the inside. So that would be 15x to the 4th. And quite honestly, that's probably good enough. We'll just leave it like that. So that would be the derivative of that problem. Let's take a look at 44. 44 is asking me to find f with 3 little marks after it, and that means f triple prime. In other words, we want to find the derivative 3 times. So let's find the first derivative. Power rule. 5 times 4 is 20. Take 1 off the power. 2 times 3 is 6. Take 1 off the power. There's my first derivative. Let's go ahead and repeat that. Second derivative. 4 times 20 is 80. Take 1 off the power. This is a constant multiple rule, so that will just be 6. And now we're ready to find that third derivative, which is what the problem is asking for. Last time, 3 times 80 is 240. Take 1 off the power. 6 is a constant now, and it just goes away, and that would be our final answer. All right, now we get to talk about implicit functions, and there's going to be 3 types on here. You can see this one is just what I would call a basic one. Number 48 has 2 y's in it, and that's the one that makes that one a little more challenging. And then number 50 is going to have a product rule in there. It's that negative 3xy. Okay, so that's going to be the 3 layers that we're going to look at for the next 3 problems. So let's go ahead and start with the easy one here, or I should say easier. It's an implicit function, and that means that the y is not by itself. And when that's the case, we start off like this. Now we're going to take the derivative of each piece. So the derivative of 2x cubed is going to be 6x squared. The derivative of 1 is 0, so that's just going to go away. And the derivative of 4y squared, well, that's going to be 8y. But remember, when this variable doesn't match this variable, we end up getting a y prime being multiplied. After you do that, you want to get the y prime by itself. So in this case, to get y prime by itself, all I would need to do is divide both sides by 8y. And if possible, you do want to reduce. So in this case, this does reduce to be 3x squared over 4y, and we are done. That would be the derivative of that one. Let's go ahead and take a look at number 48. Now, number 48, we have 2 y's in there. So let's go ahead and begin, and we'll see how that changes things. That's going to actually mean that we're going to have 2 extra steps on this problem. The first step, though, is not different. We're just going to go through and take the derivative of each piece, remembering that if there's a y on it, we take the derivative like normal, but then we multiply it by a y prime. So nothing different from the last problem yet. So now here's where the 2 new steps come in. So whenever you have 2 y primes, what you want to do is you want to find, look at your chunks. We have 3 chunks here. 1, 2, 3. We want to get all the chunks that have a y prime on one side of the equal sign and all the chunks that don't to the other side. So the only one that doesn't have a y prime is this 9x squared here. So what I'm going to do is I'm going to move this 15y squared y prime to the other side. So that's the first new step that we have to do whenever you have two y primes, or more. You could have more y primes, by the way. But the point is put them all on one side, and anything that doesn't have a y prime, put it on the other side. Now, the next new step with these types of problems is we want to factor out the y prime. So what that means is I'm going to take the y prime out of both of those terms there, those chunks. So if I take the y prime out, then it will look like this. The next thing I'm going to do is I'm going to divide this on both sides. Now, if I divide it on the left side, it goes away. And if I divide it to the right side, I would end up with y prime is equal to 9x squared over that entire thing. Now, sometimes it's possible to reduce, but remember, if you're going to reduce, whether it's a coefficient or a variable, it has to be something you can take out of all three terms. And as you guys can see, those three terms don't have anything in common. The coefficients don't have anything you could divide them by, and all the terms don't have an x, and all the terms don't have a y. So there's no reducing possible. But you do want to be looking because it will happen on occasion. Now, another thing you want to keep in mind is it's possible that because of the way that we chose to get the y prime separated, you could actually end up with a slightly different answer. You could end up with this answer instead. And the difference is that even though everything's exactly the same, everything has an opposite sign. Positive, negative, positive, negative, negative, positive. So that's possible. The reason that happens is because over here on this problem, I chose to separate the y primes by moving the 15y squared over. But somebody else might have chosen to move the 2y and the 9x by swapping them. And that would actually cause all the signs to end up being exact opposite. But they're both actually the same answer. They just look different. So keep that in mind. So you may do the problem correctly and just see that your answer is not on the paper, but there's one just like it with all the opposite signs. Well, that would be the answer to choose then. Let's go ahead and take a look at number 50. Now, what makes number 50 challenging is this guy right here. That's a product rule. And whenever I see those ones, I like, before I even begin the number 50 implicit function there, I'm just going to try to find the derivative of that product rule first. So I want to find the derivative of negative 3xy all by itself first. So this is my a, and I'm going to let y be the b. So product rule is AB, AB. All right, so a prime. The derivative of negative 3x is negative 3. B is y. A is negative 3x. And then finally b prime. Well, the derivative of y will be 1, but remember, since it's a y, we're going to put a y prime next to it. Now let's simplify that a little bit. Negative 3 times y is negative 3y. And negative 3x times 1y prime is going to be negative 3xy prime. Now that's not the answer to the problem, like this original question up here, number 50, but it is the derivative of this piece. So let's keep that in mind as we begin the problem. So here we go. Let's start with the easy stuff. So the derivative of 5x is 5. The derivative of 4 is 0, so that just goes away. Now let's find the derivative of that. Well, luckily, I already did that over here. So all I have to do is take that and plug that in over here now. So negative 3y, now plus a negative, actually, is just going to be minus. So I'll put those together now like that. And there we go. All right. Now at this point, I only have one y prime value there. So I want my y primes to be on one side and everything else to be on the other. I've got 3 chunks here. There's one chunk, there's a chunk, and there's a chunk. And as you can see, I've got a y prime here, but this guy over here doesn't have a y prime. So I'm going to get him away from the y prime term. So to do that, I'm going to add the 3y to the other side. And now, to get the y prime by itself, y prime is being multiplied by negative 3x, so to get rid of the negative 3x, I'm going to divide it out. And once again, check to see if you can reduce, but nothing reduces here. And so we're good to go there. That would be our final answer. And do be aware it's possible that this is also an answer, depending on how somebody chose to get the y prime by itself. But it's the same thing. Remember, it can be the opposite sign and still the same answer. All right. All right, so for this problem, they asked us to find this. And what this means is they want us to find the second derivative, okay? In other words, they want us to find y double prime. So that's what we're going to do. Here we go. It's an implicit function. So the first thing I'm going to do is I'm going to take the derivative of my implicit function to find out what y prime is. And once I figure out what y prime is, I'm just going to do it again to find the second derivative. So here we go. That derivative would be 4y prime. That derivative is 0, so I'm not even going to write it. That derivative is 15x squared. Next, to get the y prime by itself, I'm just going to divide both sides by 4y. And there's my first derivative. Okay? But I'm not done, because the problem wants me to find the second derivative. So, how do we do that? Well, to take the second derivative, we're just going to take the derivative again. So, we're going to do low d high minus high d low, draw a line, and square below. Now, how did I know to do that? Because it's a fraction. All right? So, low is 4y, d high is 30x, minus high is 15x squared, d low. The derivative of the bottom is 4, but let's not forget, since we're taking the derivative of this with respect to x, and that's a y, we need to put a y prime there. Draw a line and square below. Now, we are going to want to simplify these a little bit, but before we do, there's something odd that we have to do here. That's something odd. Well, let's simplify it first, and then we'll do the odd thing. So let's put these together. 4y times 30x is going to be 120yx. Next part, let's do this. 15x squared times 4 is going to be 60x squared y prime. And the bottom, squaring 4y is going to be 16y squared. Okay, so that's nice. Now let's do the weird thing. We're not going to leave this y prime here. The reason we're not going to do that is because we know what y prime equals. Y prime equals this. So what I'm going to do now is I'm going to replace the y prime with what I know y prime to be. Y prime is 15x squared over 4y. Okay, so now let's multiply these. Now you want to think of this number here as 60x squared over 1. So think of that as a fraction. Now what I'm going to do is we're going to reduce if we can. So this 4 is on the bottom and this 60 is on the top. So that 4 goes into 60 15 times. Okay? So now I've got 15x squared there instead, and just a y on the bottom here now. So the 4 is gone, the 60 is gone, and I'm left with a 15 on the top. Okay, now I'm going to go ahead and multiply this 15x squared by this 15x squared, and I'm going to get 225x squared. And then I have a 1 on the bottom here and a y on the bottom here, so I'm going to have a y on the bottom here. So top times top, bottom times bottom. The rest of it's just going to stay the same for now. Okay. Now, the next thing is we don't like having a fraction inside of a fraction. So I'm going to get rid of this little y here by multiplying this fraction by y over 1. And that way they cancel. And I'm allowed to do that so long as I multiply every other chunk in here by a y. So if I do that, I have y double prime is equal to 120 y squared x minus 225x squared over 16y cubed. And once again, you want to see if you can reduce. This thing here can only be divided by 15, 5, or 3. So, but 15, 5, or 3 don't go into 16. So I know I can't reduce anything out of the coefficients. This term doesn't have an x, so I can't divide out any x's. And this term up here doesn't have a y, so I can't divide out any y's. I would have to be able to divide something out of all 3 if I wanted to reduce it, and I can't. So this is my final answer. All right, let's go ahead and take a look at, I accidentally did number 51, darn it. But you guys can use that to do 52. Let's go ahead and take a look at number 54 now. 54 is asking me to find the derivative at a specific point. So this is another implicit function. So we're going to start off like this. The derivative of 1 is 0. The derivative of 5x cubed is 15x squared. And the derivative of y squared is going to be 2y times y prime because that one is a y. Next, we want to get the y prime by itself. So I'm going to add this 2y prime to the other side. And that will leave me with 2y y prime equals 15x squared. So I've got my primes and non-primes separated. And now I'm going to go ahead and divide everything by 2y to get that y prime completely by itself. And I have my derivative. But this problem is asking me to do something special. We've already done a problem like this on the study guide. What's special about this one is they want me to actually plug a number in. They want me to plug 1 in for x and 2 in for y. So let's do that. That would give me 15 over 4. And so what we're doing is we're finding the actual slope, or the instantaneous rate of change of that implicit function at one specific point. Right? All right, so I want to find f inverse of 5. I want to find the derivative of f inverse of 5, actually. Let me correct that. That's not typed correctly. Just a moment. Okay, so I didn't want to find just f inverse of 5. I wanted to find the derivative of f inverse of 5. So now it's written correctly. So there's a formula for finding f inverse of number. It's going to be 1 over f prime of f inverse of 5. Okay? So that's our setup. So the first thing we want to do is we want to figure out what is f inverse of 5. Well, if f of 0 equals 5, then by the definition of an inverse, f inverse of 5 would have to equal 0. And therefore I can replace the f inverse of 5 inside the parentheses there with 0. Now I want to find out what is f prime of 0. To do that, I need to take the derivative of my function here. And that's going to be 28x to the 6th plus 2. And then I want to plug 0 into it. Now 0 to the 6th power is 0. 0 times 28 is 0. So I'm just left with 2. And my final answer will be 1 over 2. Okay? So step 1, write your formula. Step 2, find the inverse value using the definition of an inverse. Step 3, find the derivative and plug in the number they're asking for, and then plug it in, and then you're all done. All right? Let's go ahead and jump up to number 57 here. There's a lot going on this particular problem. Now, I don't think I'm going to do every one of these. Let's see, which ones should I do? I think you guys will probably do okay with numbers 1 through 4. We've done that in class a little while ago, but I'll do parts 5 and 6 because I remember those ones when we did them in class, we struggled a little bit. So let's go ahead and do part 5 together. All right? So if h is equal to f of x squared, then whenever I want to find my derivative, we have to know what rule to use. Well, this is going to be a chain rule because I have an outside function and I have an inside function. So the derivative of the outside is a power rule, so I'm going to move the 2 to the front, and I'm going to take 1 off the power, and then I'm going to leave the inside exactly the same. Next, the derivative of the inside is just going to be f prime of x. Now the problem is asking me to plug 2 in, so I'm going to plug 2 into my function there. All right, from here we're going to use our table. What is f of 2? F of 2 is 2. So I'm going to end up with 2 times 2 to the first power. Next, we need to find f prime of 2. F prime of 2 is 3/2. So now I've got 2 times 2 to the first power, which is 4, times 3 over 2. You can think of that as 4 over 1. You could reduce the 2 into the 4, and you end up with 6 over 1, which is just 6. All right, let's go ahead and take a look at part 6 now. Part 6, my function, is another composite function. So once again, we're going to be doing the chain rule. My outside function is the f. My inside function is the g. So when I take my derivative, the derivative of the outside is f prime, and we'll leave the inside the same. Multiplied by the derivative of the inside, that would be g prime. And for this particular problem, we're plugging in a 4. So first of all, let's find out what g of 4 is. G of 4 is 1. So now that's going to become f prime of 1. Now we need to figure out what's f prime of 1. F prime of 1 is 1. G prime of 4 is negative 1. And so my final answer will be negative 1. All right, last one here. Using the table that we just used before, we're going to find f inverse prime of 3. So I'm going to go back to my chart here. I'm looking for f inverse prime 3. Well, we have a formula for that. When you're taking the derivative of an inverse, it's 1 over f prime of f inverse of 3. So I want to know what this is first. What is f inverse of 3? Well, if f inverse of 3 equals question mark, that means f of question mark equals 3. That's the definition of an inverse. So I want to know what value of x has an f value of 3. So which of these x values has an f value of 3? Well, f has a value of 3 right here, and so the x value that goes there would be a 4. So that means this is a 4, which means this is a 4, which means this is a 4. And so we have 1 over f prime of 4. Now, using our table once again, I want to find where x equals 4, and I want to find what f prime is at that point. So, x equals 4 right here, and f prime is negative 1. So I have 1 over negative 1, which is negative 1. Final answer. All right? So these are the types of questions that you guys will see in the multiple choice section of your exam. Give or take a few. Obviously, I can't give you that many questions. You'd never finish on time. But these are the types of questions that are possible to come up. So hopefully that was helpful. And next thing we'll look at is your FRQs. So if you need help with your FRQ study guide, we can go through that too.